Hello everyone, welcome back to ISDTWF video. What you are seeing is a picture of the original Apple 16 kilobyte language card, which was the first expansion for the Apple II and Apple II Plus computers that added 16 kilobytes of additional RAM and kernel upgrade for the original Apple II that could change the last 4 kilobytes of firmware to allow the original Apple II to boot from disk like the later Apple II Plus could do. So my Apple II Plus didn't come with this card, but I'm sure it was fitted at one time, and we'll see later why I think so. This card is not easy to find, and anyway I would rather design something equivalent of my own to allow me to have a 16 kilobyte expansion, and so I could use ProDOS and some other programs on with my new europlus that I repaired recently. So this video is about reverse engineering this card and making my own replacement, not looking anything like this, but just using some more modern components and approach. So let's see how it did and how it works. Of course, with a little search on the internet we can find both the original manual of the language card and the schematic from Apple. I will link both on the description of this video. Of course, these are the best starting point when reverse engineering the card. Okay, first let's see how the additional 16 kilobytes of RAM will be mapped on the 6502 memory space. As you may know, 6502 can only address 64 kilobytes of memory at the same time, because it has only 16 address lines. So on a Apple II onboard RAM, which is up to 48 kilobytes, starts at 0 and ends at BFFF address space, which is 49,151 in decimal. At C000 starts a 4 kilobyte space dedicated to onboard input output and the expansion cards addressing. So from C000 to CFFF is IO space, which is not usable for any other RAM expansion. The ROM, onboard ROM on the Apple II starts at D0 and ends at FFFF, D000 of course. So looking at the map on the screen, the situation is the second, when you insert the original Apple II 16 kilobytes language card, the map at power on is the second from the right, because the onboard EEPROM replaces the last 2 kilobytes of the onboard Apple II ROM, which starts at F800 and ends at FFFF. On my card I made this ROM replacement optional with a jumper. So at boot, with the jumper removed in the off position, I mean, the situation is ROM on board Apple II ROM from D0 to FF, and RAM disabled and not write enabled. The RAM can be write enabled without being read enabled, so we can read from ROM and write to RAM at the same time if we enable the write to the underlying RAM. So the RAM can be enabled in place of the onboard ROM in two different configuration actually. Since the available space, if we disable all the ROMs, is only 12 kilobytes, and the additional RAM is 16 kilobytes. There are two possible configurations. The upper RAM is always mapped from E000 to FFFF, and the second 8 kilobyte can be split in two banks and mapped from D000 to DFFF. So the upper 8 kilobytes are always mapped, and the lower 8 kilobyte can be mapped in two banks of 4 kilobyte each. That's because the C0 to CF space, which is the other 4 kilobytes missing, is always mapped to IO. This is very well explained in the manual page of the language card. The control codes independently do three things: write protect or write enable the RAM of the language card, select or deselect RAM read, and select the first or second 4K bank of RAM for the address space D000 to DFFF. This bank selection is necessary because the address space C000 to CFFF is taken up by input-output devices and routines, so that only 12 kilobytes of address space is available to address 16 kilobytes of RAM. By locating two 4 kilobytes banks of RAM in the address space D000 to DFFF and switching between them with the control codes, 8 kilobytes of memory can be addressed with 4 kilobytes of address space. The remaining 8 kilobyte section from E000 to FFFF or RAM in the language card is reached without bank switching. By the way, the manual codes, control codes, actual RAM location, which are mapped to the IO slot where the language card is inserted, the slot 0 in this case. So they are actually locations in the 6502 space that have to be read in order to change the configuration of the language card. So control codes are really just locations in the 6502 address space. All the reasons why I decided to design my own replacement and not copying the original circuit derive from the fact that the original design uses dynamic RAM. As you can see on the photo of the original board, on rows 1 and 2, the leftmost two rows of chips, there are 9 chips, dynamic RAM chips, 1 bit for by 16 kilobytes. So 8 of these are needed to compose the 16 kilobytes of RAM, and one of them is need to be extracted from the Apple II motherboard and inserted in an empty socket on the board. And as you can see on the bottom left, there is a ribbon cable that has an header that goes into the socket of the chip we just extracted. And the reason is that dynamic RAM needs to be refreshed, and it needs address multiplexers to work, and a two-phase select with row address select and column address select. All the circuit from refreshes are really on the Apple II motherboard, and also the address multiplexer chips are on the Apple II motherboard. So the card designer cleverly used the refresh and the multiplexing from the motherboard, but they needed to bring the signals to the board because they are not present on the expansion connector, and to bring the signals needed to refresh and multiplex addresses on the RAMs. They thought to extract one chip from the motherboard, from the Apple II motherboard, and get to the needed signals with the ribbon connector and the header. And so dynamic RAM is large, needs many chips, is not manufactured anymore, and what you find as old stock is expensive, and actually 8 chips would cost more than what I spent with the PCB and all the parts of my replacement board. And my limited stock of 16 kilobit dynamic RAM is best used to repair old computers that need this kind of RAM, instead of making an expansion board that can be made with different chips. And the board with static RAM, that is what I used, can be made with current made chips and SMD chips too. And it takes only 2 chips to go to the 16 kilobytes. It doesn't need any pickup of refresh signals from another socket on the motherboard. All the needed signals can be found on the connector, the expansion connector, as you can see as the part of the schematics that I drawn with my expansion board. The configuration bit part of my schematic is actually a gate-by-gate replica of the original language card, unless on the first revision of my PCB I thought I could spare one gate with respect to the original schematic, but I realized soon after ordering the first PCB that this optimization would actually cause the Apple II not to start with my board, because the gate was really needed to allow the ROM to be selected at power on with my so-called optimization. Now the RAM would be selected at power on, and the machine would never start because the RAM content would be random at power on, of course. So I had to make some patches to my first revision PCB, and another patch I needed was actually discovered when first I tried the board on my Apple II, and that was just a little design error on my part, because I forgot some golden rules of TTL design. Actually, the rule was you never pull down with a resistor a TTL input, a real TTL input. I mostly used CMOS gates from the 74HCT family, but also used real 74LS gates, and you don't really want to pull down an input of a real TTL gate. I mean, of course, it's perfectly fine to tie an input to ground, but if you want to drive an input high with a pull down with another gate, you cannot really do that with another LS gate. And finally, I added 3 LEDs to visually see the status of the switches, the configuration switches of the card. So the red LED will be on when the RAM is write enabled. The yellow LED will be on when the RAM is read enabled, and of course in this case the ROMs are disabled, and the green LED would be on when the second bank of the lower RAM is enabled, and it will be off when the first bank is enabled. So let's make some simple tests. Control reset and control -151. So if I read from C082, well, the ROM is disabled at boot, and I can change the I should select the bank. Yeah, so the green LED it's light because I selected another bank, but read is always from ROM. I can write enable the RAM reading twice from seed 081 again. Yes, so the red LED come home. But if I enable the RAM in read mode at this time, since there is nothing on the RAM, it's just started the machine with random contents. So if I enable the RAM read, so the red LED will go off, and yellow LED will light at this time. Yes, it does, but the machine solidly crashes. It doesn't respond to anything, so it must be because of course the monitor and the basic are running from ROMs. So I just disabled all those onboard ROMs, and machine crashed. Cannot execute any meaningful thing from the RAM at the moment. So let's see a simple test to enable the RAM and not making the machine crash. So as we have seen, the Prodos starts correctly, loads the card, and it seems to work fine. But I thought I will give you just a little example of both 6502 old style assembly programming, and just a little insight of about how this card is supposed to work with the switches, software switches, and so on. To do that, I found my first book of 6502 programming, which is in Italian. I think I bought this one in 1982 or 1983, early 1983, to better use my VIC-20, because with 3 kilobytes of free space, BASIC was really not doing much on that machine. And this is a precious book to me because I started real programming with this. And using this as a reference, there are instructions, cycles, calls, and everything, so I can handle assemble a program as I used to do before having a real assembly program on a C64 when I had it. So the program is this one. Really simple. I first wrote what I wanted to do, and then added the hexadecimal equivalent to the instructions, and I chose 800.0800 as a start address for the program in the main memory. I've seen this is a good place on an Apple II to run an assembly program. So what we want to do is copy all the ROM space into the RAM. ROM space starts at D000, and on a 6502 the addresses need to be reversed. So in the last byte of a page 0 location, we write the most significant byte of the address, D0, and I choose just FE and FF, the last two location of page 0, to store the address. I don't know if they are used by BASIC or something, but I think it works. So on the first byte we write 00. We load on register Y, which is an 8-bit index register on the 6502. So I loaded the D0 first and stored on FF page 0. Loaded 00 and stored in FE. Why I choose to load 00 after the D0 is because I will use register Y as an index, and it must start with 0. So I don't have to put 0 again if I first use 0 and then store D0. Then what we do is load the accumulator, which is another 8-bit register, from the location that is contained in the location FE in page 0. So FE contains 00D0, which is D000 actually. And then add at the content of this location, we add the content of register Y, which starts with 0 at this moment. And same thing, we load the accumulator with the location we just calculated this way, and we store the accumulator content to the same location. But since we have seen that we can read from ROM and write to RAM, this load accumulator will pick up a value from the ROM, and this store instruction will store the same value to the RAM at the same address. So far so good. So after doing this, we decrement the Y register, So since we start at 0, it now becomes, it rolls over and it becomes FF. And if it's not 0, this instruction tells the processor to check if the last instruction produced a 0 result. So branch if not equal means if the result was on the previous instruction was not 0, we jump back in this case to 0808. I mean 0808 is the load again. So we do this cycle, loading, storing until the Y returns to 0. When the Y returns to 0, the Y register, we increment the location FF. FF contained that originally the first page we want to copy. So we increment and this becomes D1. So we start copying the D1 page again. We start on the cycle. So again, if this instruction didn't produce the 0 result into the FF location this time, not this one looks for a 0 into the Y register. This one, since we incremented the FF page 0 location, we jump back to again 0808 until the location at FF contains 0. So we jump back and do another 256 cycle, copying page D1, then increment again. So we copy page D2, D3, D4, and so on. And after we copy page FF, which is the last page of the ROM, this increment instruction will produce a 0 in location FF. And so we don't jump anymore to this 0808 location, and we execute a break, which is an soft interrupt instruction that will bring us back to the machine language monitor. And so last thing to do is to enable write flag on the expansion. I will read 2 times the C081 location, and to read enable and write disable the RAM, I will read the C080 1 time. So we are ready to test this simple program and see if it works. We'll copy all the content of the ROMs to the expansion RAM, and after this reading from C080, the RAM will be enabled and the system will run from RAM, unless, as we have seen, if I enable the RAM without copying anything, the machine just crashes. So in order to demonstrate the program, let's start the Apple II, hit Control Reset, because we don't want to load anything from disk, and call -151 to go to the monitor, and let's check what is on the page 0 location that we had chosen. It's just looks like two random values, I don't know. And let's enter our program by typing every byte starting from 800. So now tell the monitor to show us the assembly starting from 800, adding L at the location, so we can check LDY D0 store to FF, LDY 0 store to E, right? Load store decrement Y not equal 0800 increment. Yes, looks like correct. And of course, for this to work, I have first to enable the write signal on the RAM, and that would be with two reads at C081. So first one, second one, yeah, and the red LED comes on. So now I can start the program. 800 go, and it's very fast, of course. That's a good thing of machine language. And at this point I can read enable the RAM and also at the same time disabling the write enable. So if I read the C080, the red LED, which is the write enable, should go off, and the yellow LED, which is reading from RAM enable, should come on. And yes, it is. And the machine didn't crash, as you have seen. The monitor still works. If I exit on basic, Control C, return, basic is still here, but we are always reading from the expansion RAM. Onboard ROMs are disabled entirely at this moment. Basic works. And also I think the video ends here. For watching. So I hope you enjoyed this deep dive into the 6502 assembly and this Apple II expansion. Now I have 64 K of RAM Apple II europlus to play with, and I will probably make some other cards for this machine, like maybe a color PAL color card, or who knows, I would see. So I hope you enjoyed. Thank you for watching.